Okay, let's unpack this. Take a quick look around you. I mean, from the smart device you're listening on to the roads you drive, even the stuff in your fridge, everything you interact with every single day has been designed.
Mm. Meticulously.
Right. There's this unseen hand of engineering shaping our world. And the thought that goes into it is, well, it's pretty profound. So today, we're taking a deep dive into that fascinating world, the engineering design process. It's the systematic approach engineers use to create, innovate, and, keep improving everything around us.
And our mission for you, our listener, is to kind of pull out the core insights from these engineering fundamentals textbook excerpts you've shared. We're aiming to go beyond just what engineers do, to
Yeah.
really get how they think and why their method, this systematic way, is so incredibly crucial. We'll walk through the steps, the big things they consider, and even touch on like the human side, teamwork, sustainability,
Yeah.
that stuff.
Because here's where it gets really interesting, I think. This isn't just about formulas or, crunching numbers.
Not at all.
It's about a structured way to solve real-world problems, problems that impact all of us every single day. So let's start with the blueprint, the kind of core phases engineers follow. You often see them listed as steps, but it's rarely just a straight line, is it?
No, definitely not.
We're talking about recognizing a need, really digging into defining the problem, doing the research, brainstorming solutions, conceptualizing.
Yeah, conceptualizing.
Then synthesizing those ideas, evaluating them carefully, optimizing the best one, and finally presenting that solution.
That's the list. But it's so important to remember, like you said, it's iterative, very iterative. Engineers often find themselves looping back to earlier stages. Maybe a client changes something,
Yeah, happens all the time, I bet.
or just new information pops up.
Mm-hmm.
And those progress reports, they aren't just tacked on at the end. You're giving updates, oral, written, pretty much throughout the process. It's woven in.
Okay, so that first spark, recognizing the need, it feels like that's just everywhere. Think about how products are always changing. Cars get smarter, appliances talk to each other.
Phones practically reinvent themselves every year, yeah.
Exactly.
There's this saying, you hear it a lot. Every time someone complains, there's an opportunity for a product or service. And the need can bubble up from inside a company, or maybe an engineer just sees something.
Or a client comes knocking.
Right. Or very often, yeah,
Yeah.
directly from a client with a specific challenge they need help with.
And that takes us right to step 2, problem definition and understanding. I've heard this called the most important step.
Oh, easily. Many people say that.
And it makes sense, right? If you don't fully get the problem, if you don't really understand what the client actually needs, well, any solution you cook up might just miss the mark completely.
Exactly. This whole phase is just asking question after question. What's the budget? Any material limits? Size constraints? When's it due? How many do you need? And what's interesting is each answer usually sparks another question.
So it's like peeling an onion.
Kind of, yeah.
Yeah.
You keep refining, clarifying, digging deeper until the actual problem is crystal clear, and make sure you're solving the right puzzle,
And this isn't usually a solo mission, is it? The sources really stress how collaborative engineering is. Big, complex problems almost always get broken down for teams.
Absolutely, which means those interpersonal skills, communication, they're not just nice to haves, they're essential. Especially now with global markets, you might have parts coming from different countries, different companies.
Wow, yeah. Getting everything to mesh perfectly must take some serious coordination.
It really does.
Okay, so once that problem is properly defined, step 3 kicks in. Research and preparation. Basically, gathering info.
Right, and the big idea here is simple. Avoid reinventing the wheel. Why start from absolute scratch if someone's already figured part of it out?
Makes sense.
So engineers check existing products, look inside their own company for components or knowledge, maybe team up with other firms, and obviously use the internet, databases, all that. The key is gathering relevant info efficiently and keeping it organized.
Building on what's already known.
Precisely.
Then we hit step 4, conceptualization. This sounds like the fun part, the creative brainstorming phase.
It definitely can be. It's all about generating a whole bunch of potential solutions, different concepts, without getting too bogged down in tiny details right away. You want quantity of ideas initially.
So breadth over depth at this stage.
Exactly. The goal is to develop several alternative solutions. Engineers do just enough preliminary analysis, maybe some rough calculations, to see if these concepts even have potential merit. They're asking, like, could this actually work if we pursued it?
Gotcha.
And this is also where things like time management become really important. You might use milestone charts, things like that, to keep the project on track.
Okay, so you've brainstormed, you've got these concepts floating around. How do engineers actually turn those into something real, something that works? This feels like where the refinement really starts.
Yeah, you're moving into step 5, synthesis. This is where the details really start to take shape. Now you're doing the serious calculations, running computer models, maybe simulations.
Getting specific.
Very specific. Narrowing down the material choices, figuring out the exact size of components, how things will actually be made, fabrication methods. And crucially, this is where you have to make sure everything complies with the relevant codes and standards. That becomes a huge factor.
Right, the rules of the road, basically.
Then comes step 6, evaluation. Here, you're analyzing the potential solutions in even more detail, identifying the really critical design parameters, understanding how changing one thing affects everything else.
So more analysis, more number crunching.
Definitely.
Yeah.
And getting those calculations right is critical. If there's still uncertainty, maybe about how a material behaves or how a part will perform under stress, that's when you might need to do actual experiments, build and test working models or prototypes.
To see it in action.
Exactly. The whole point here is to rigorously compare the alternatives and identify the single best solution from the concepts you generated earlier.
Okay, and this leads us to step 7, optimization, which you mentioned. This sounds like where it gets really interesting. It's not just functional, it's better than functional.
Precisely.
Yeah.
Optimization is about making it the best possible solution according to some specific criterion. Maybe you want to minimize the weight or maximize the strength or maybe minimize the cost. Our sources draw this distinction. A functional design just meets the basic requirements. It works.
Check the box.
Right. But an optimized design is the best possible solution based on what you decided was most important. Think about designing a ladder, steel ladder. Totally functional, probably strong.
Sure.
But if your optimizing criterion is minimizing weight, you'd probably end up designing an aluminum ladder. It still meets the strength needs, but it's way lighter. That's optimization in action.
That's a great example. Makes sense.
And here's the tricky part. Optimizing just one piece of a system doesn't automatically optimize the whole thing. Like with a refrigerator, just making the compressor super efficient doesn't mean the entire fridge is now optimized. You have to look at the system level.
Ah, okay. The bigger picture.
Exactly. Historically, this was a lot of back and forth, trial and error, analyze, tweak, analyze again. Now, engineers have powerful software and programming techniques to help find these optimal solutions much more systematically.
Let's make this concrete with that storage tank example from the sources. This really shows the trade-offs, right?
It does. So imagine you've got a fixed budget, $1,680, and a limited floor space, 90 square feet.
Constraints. Always constraints.
Always. And you need to maximize your storage volume using tanks from 2 different suppliers. Tank A holds 16 cubic feet, costs $120, takes up 7.5 square feet. Tank B holds more, 24 cubic feet, but costs more, $240, and needs 10 square feet.
So more capacity, but higher cost and bigger footprint for B.
Right. What's cool is how engineers translate this into math. You set up an objective function what you want to maximize, which is total volume. Z equals 16 times the number of A tanks plus 24 times the number of B tanks. Then you define your constraints. The budget constraint, total cost can't exceed $1,680, and the space constraint, total area can't exceed 90 cent/QF. Plus, you can't have negative tanks, obviously.
Right.
Using techniques like linear programming, you map out the feasible region, all the combinations of tanks that satisfy both constraints. Then you check the corner points of this region to see which combination gives the maximum value for your objective function, the volume.
And the math points to the best mix.
Yep. In this specific case, the math shows that buying 8 of tank A and 3 of tank B hits the sweet spot. It uses the budget and space effectively and gives you the maximum possible storage, 200 cubic feet. It's a neat way to see how complex decisions with trade-offs can be broken down and solved mathematically.
That's fascinating. Okay, so the design is optimized, the numbers are crunched, best solution identified. Now what? You have to tell someone.
Exactly. Step 8, presentation. Communicating that final solution effectively is key. This could be to your boss, other team inside the company, or maybe an external client.
And it takes different forms, I assume.
Oh, yeah. It could be anything from a short memo summarizing the results to a huge detailed technical report packed with graphs, charts, calculations, engineering drawings, the works.
So those communication skills we talked about earlier are critical here too.
Absolutely critical. Engineers need solid people skills. You're interacting with sales, marketing, manufacturing, other engineers. You need to be able to explain your design clearly and persuasively to all sorts of different audiences.
Makes sense. Now, shifting gears slightly, our sources really emphasize sustainability as a huge focus these days. We hear that word a lot, but what does it really mean in an engineering context?
Well, the classic definition, and the one in our sources, is designing and developing in a way that meets the needs of the present without compromising the ability of future generations to meet their own needs.
Okay, thinking long term.
Exactly. And its importance is just skyrocketing. You've got global trends, major environmental worries, and the simple fact that, the planet's resources aren't infinite. Engineers are now expected not just to improve living standards or healthcare.
But to do it responsibly.
Precisely. They need to actively tackle environmental and sustainability challenges, thinking about how resource use connects to everything: environmental impact, social factors, ethics, technical feasibility, and of course, economics.
And this isn't just a nice to have anymore, is it? The sources mention some pretty stark figures, like the world using resources faster than the planet can regenerate them.
Yeah, something like 20% more, according to the text. Plus, we're seeing the impacts: rising energy costs, more extreme weather, sea levels creeping up. It definitely forces the question: how do engineers move from just traditional design thinking to actually leading the way on sustainable development?
So what's being done? Are there specific initiatives?
Oh, definitely. Major engineering bodies like ACE for civil engineers and IE for electrical and electronics engineers are pushing sustainability education hard. ACE even calls it a top priority. There are global projects like IE's GEOS, which is basically a huge Earth monitoring system to help guide sustainable practices.
And things like green building certifications.
Exactly.
Mm.
Like the U.S. Green Building Council's LED system, Leadership in Energy and Environmental Design. That's a big one, recognized internationally. It verifies how well a building performs on things like energy use, water efficiency, CO2 emissions, indoor air quality, resource use.
That sounds pretty comprehensive.
It is. And it provides a clear benchmark.
There's also that example of Lauren Hine in the materials. Her shift in thinking sounds really significant.
Yeah, that's a great illustration. She moves from focusing on end-of-pipe solutions, basically, dealing with waste after it's created, to thinking about how to design the problems out from the start, using approaches like green chemistry and cradle-to-cradle design.
So being proactive rather than reactive.
Exactly. And her experience showed it wasn't just better for the environment, it actually saved money by cutting waste costs. And maybe even more importantly, it drove innovation, leading to better, smarter products. It shows sustainability and good business can go hand in hand.
That's powerful. Okay, let's also touch on those everyday practical constraints. Engineering economics and choosing the right materials. Can't forget the bottom line, right?
Never. Cost is always a critical factor. I mean, you could design the most amazing gadget ever, but if it costs a fortune to make, nobody will buy it, and it won't be profitable. Simple as that.
So cost is a constant design constraint.
Absolutely. And right alongside it is material selection. That's another huge decision point. Engineers need to understand a whole range of material properties. Things like electrical properties like resistivity. Why use copper for wires and plastic for insulation? It comes down to that property.
Okay.
Then you have mechanical properties.
Right.
Like density, why use aluminum instead of steel in aircraft? Strength-weight ratio is key there. Stiffness, which is modulus of elasticity. How much it resists twisting, modulus of rigidity. How much load it can take before failing. That's tensile strength.
Lots of specific terms there.
Yeah, and they matter. Like compression strength is vital for concrete. Modulus of resilience, how much energy it absorbs without permanent damage. Modulus of toughness, how it handles overloading before it actually breaks.
Wow. Okay, what else?
Thermal properties are huge too. How much does it expand when heated? Thermal expansion, how well does it conduct heat? Thermal conductivity, think heat sinks versus insulation. Heat capacity, how much heat it can store.
Crucial for anything involving temperature changes.
Definitely. And then for fluids, you worry about things like viscosity, how easily it flows. Think water versus thick motor oil. Vapor pressure, how quickly it evaporates. Bulk modulus, how much you can compress it.
And engineers need to know all these specific values for the materials they might use?
Well, they don't memorize everything, but they know where to find it. Manufacturers provide detailed data sheets with all these specific values. And using the correct values is absolutely essential for accurate calculations and successful designs. You can't just guess.
Right, precision matters. So we've established engineers work collaboratively. They aren't lone wolves. They're part of teams working within rules.
Exactly. A design team, fundamentally, is a group of people with different complementary skills, all working towards the same goal. Good teams need openness, respect, and the team's goals have to come before any individual's agenda.
Makes sense.
The sources even mention Bilbin's team roles, which is interesting. Like, you often have an organizer type who keeps things on track, clarifies goals, then maybe a creator, the ideas person, the problem solver, an evaluator who's good at judging ideas objectively, and a finisher, the detail-oriented one making sure everything gets done right and on time.
Recognizing different strengths within the team.
Yeah, and understanding that a mix is usually best.
And within any team, let's face it, you're going to have disagreements, conflicts. How do engineers handle that?
Well, conflict is pretty much inevitable when you have passionate people working together. The sources mentioned a few approaches like avoiding it, or just giving in, accommodating, or splitting the difference, compromising.
But those don't sound ideal.
They often aren't. The most effective approach highlighted is the collaborative one. Treat the conflict itself as just another problem for the team to solve together. This takes really good communication, active listening, really trying to understand the other person's viewpoint, asking clarifying questions. It's about finding a win-win, not just winning the argument.
Solving the problem, not beating the person.
That's a good way to put it.
Yeah.
And beyond teamwork dynamics, engineers also rely heavily on things like project scheduling tools to make sure they hit deadlines and stay within budget. And they often use things like evaluation tables, systematically scoring different design concepts against key criteria to make objective comparisons when choosing the best path forward.
Okay, so you've got this great optimized idea developed by the team. How do you protect it? Let's talk intellectual property patents, trademarks, copyrights.
Right. Protecting IP is super important because it's what encourages people and companies to innovate in the first place. If anyone could just copy your invention immediately, why bother investing all the time and money?
Good point. So what's the difference between them? Patent, trademark, copyright.
Okay, so a patent gives the inventor the right to exclude others from making, using, or selling their invention for a certain period, typically 20 years, for a new utility patent in the U.S. Now notice I said exclude others. It doesn't automatically give the inventor the right to use it themselves. Maybe someone else has a broader patent covering it, but it lets them stop competitors.
Okay, so it's a shield, not necessarily a sword.
Kind of, yeah. Then a trademark is about branding.
Oh.
It's a name, a word, a symbol. Think logos, brand names that distinguishes products from one company from those of another, like Coke versus Pepsi. It stops others from using the same mark confusingly, but it doesn't stop them from making a similar product, like another cola drink. And a service mark is the same idea, but for services instead of products.
Got it. And copyright.
Copyright protects original works of authorship, things like books, music, software code, architectural drawings, movies. It protects the specific form of expression, not the underlying idea itself. So you can't photocopy my physics textbook, but you're perfectly free to write your own physics textbook, explaining the same concepts in your own words.
Ah, expression versus idea.
Exactly. And copyright protection usually lasts a long time, typically the author's life, plus 70 years. These three, patent, trademark, copyright, are the main pillars of IP protection.
Okay, that clarifies things. So beyond protecting ideas, what about the rules engineers follow in their actual work? Standards and codes seem huge.
Oh, they're absolutely fundamental. What does this all mean? It means these aren't just annoying bits of red tape. Engineering standards and codes are essential for safety, reliability, and just make sure things work together, especially in our globalized world.
How so? Give me an example.
Well, think about your car. It has thousands of parts, probably made by hundreds of different suppliers all over the world. Standards ensure that a bolt made in Germany actually fits a part made in Japan. They ensure interoperability.
Right, things have to fit.
They absolutely do.
Yeah.
And beyond just fitting together, standards are critical for safety. Think building codes ensuring structures don't collapse, standards for safe drinking water, regulations for transportation systems. Imagine the chaos without them. Even something simple, like the size of a credit card that's an ISO standard, so it works in machines anywhere. Contrast that with, say, shoe sizes or shirt sizes, which still vary between the US and Europe. Now imagine that lack of standardization for complex industrial components. It would be a nightmare.
Yeah, okay, I see the point. And there are big organizations that set these standards.
Yes, lots of them. Our sources mention several key ones. ANSI, the American National Standards Institute, ASTM, the American Society for Testing and Materials, which develops tons of standards for materials and products, and FPA, National Fire Protection Association, vital for fire safety codes. UL, Underwriters Laboratories, you see their mark on electrical appliances for safety testing. ISO, the International Organization for Standardization, which works globally. And the CE marking you see on products sold in Europe. These groups are crucial.
They're like the guardians of consistency and safety.
In a way, yes. And the standards can get incredibly specific. Remember the tire example?
Vaguely, remind me.
The marking on a tire, like P22555R1694H. That's not just random letters and numbers. Each part conforms to a standard. P for passenger car, the 2-25 is the width in millimeters, 55 is the aspect ratio, height to width. R means radial construction, 16 is the wheel diameter in inches, 94 is the load index, and H is a speed rating. All standardized so consumers and manufacturers know exactly what they're dealing with.
Wow, that's a lot packed into one code.
It is. And then you have critical environmental standards, too.
Yeah.
The EPA, the Environmental Protection Agency in the U.S., sets standards for drinking water, for instance. They have goal levels, MCLGs, and legally enforceable limits, MCLs, for various contaminants.
Protecting public health.
Directly. Same for air quality. The Clean Air Act mandates the EPA to regulate major outdoor air pollutants, carbon monoxide, lead, nitrogen dioxide, ozone, sulfur dioxide, and particulate matter. These come from factories, cars, power plants, even natural sources.
And have those standards helped?
Actually, yes. The compelling thing noted in the sources is that even though the U.S. population has grown and people drive more miles, the actual emissions of these major pollutants have decreased significantly over the last few decades. That's a direct result of engineering innovations, cleaner engines, better industrial processes driven by these regulations.
That's encouraging. What about indoor air?
Indoor air, that's often more polluted than outdoor air, sometimes 2 to 5 times higher, believe it or not.
Really? Why?
Several factors contribute. Modern energy-efficient buildings are often sealed very tightly, which traps pollutants inside. We use lots of synthetic materials in furniture, carpets, cleaning products, and these can release chemicals, off-gassing. This can lead to symptoms like headaches, fatigue, irritated eyes, sometimes called sick building syndrome.
So what do engineers do about that?
They tackle it from multiple angles, trying to eliminate or substitute the sources of pollution, ensuring proper ventilation design, bringing in fresh air and exhausting stale air, and using air cleaning technologies like filters or purifiers.
Okay. So we've really journeyed through this whole engineering design world, haven't we? From spotting a problem, defining it, brainstorming, refining, optimizing, making it sustainable, all while juggling materials, teamwork, costs, and these vital standards. It's intricate.
It really is.
Yeah.
And if we sort of connect this back to the bigger picture, it's so clear that what engineers do isn't just technical wizardry in a vacuum. It's deeply woven into society's needs, economic realities, and increasingly our environmental responsibilities. That constant cycle of learning, adapting, iterating, innovating, that's really the heart of it, I think.
It's a continuous improvement loop, driven by real-world needs and constraints.
Exactly.
So here's a final thought for you, our listener. Next time you pick up, well, anything, your phone, your coffee mug, or use a service like streaming video, just take a second. Consider the countless design decisions, the iterations, the teamwork, the standards, the optimization that went into making that thing possible, making it work the way it does. What hidden engineering choices are shaping your experience right now? And maybe, how might you look at it with an engineer's eye, looking for that elegant improvement?